Lesson 5. The event A and B. When do you multiply probabilities? Well, let's look at situation 1. Drawing 2 balls from the pot without replacement. So a ball is randomly selected from the pot and is not replaced. Then a second ball is drawn. We're going to define the following events. F would be that the first ball is white, and then F bar would be that the first ball is not white. S is going to be that the second ball is white. S bar would be that the first ball is not white. As we can see, we've got 2 white balls and 1 black ball. So to find the probability of the first ball being white would just be 2 out of 3. Now we're not replacing that first ball, so now we have a new sample space. The sample space now consists of 1 white ball and 1 black ball. So the second part here, we have the probability of the second ball being white given that's that vertical bar there, given that. So the probability of the second ball being white given that the first ball is white would now be 1/2. Now, to find the probability of the first and second would be to multiply those two together. And that would be 2/3 times 1/2, which equals 1/3. Now I'm just going to complete this tree diagram that we have to the right here. So we already have that for the first ball would be 2/3 white, which would leave 1/3 black. Now, if we chose a white ball, we do have now a new sample space with 1 white and 1 black. So to pick a white ball would be 1/2, and to pick a black ball would be 1/2. With the second line, where we had chosen a black ball, we now only have 2 white balls. So we have a 100% chance of picking a white ball the second time, so that would be 2 out of 2. And to pick a black ball, it would be 0 out of 2. So along the bottom, what I have just written is what it would be for each one of those lines. So a white ball and a white ball would be 2 out of 6. A white ball and a black ball would be 2 out of 6. A black and white would be 2 out of 6. And a black would be 0 out of 6. The events F and S are called dependent because the probability of the second ball being white would depend on what happened with the first one occurring. Situation 2. We're now drawing 2 balls with replacement. So a ball is randomly selected from the pot and it is replaced. Then a second ball is drawn. So we have the same sets as we had before. F being the first ball is white, S is the second ball is white. Now, when we're looking for the probability of the first ball being white, it's going to be the same as it was before, 2 out of 3. But now we're replacing that white ball, so we're right back to having 3 balls in there, 2 white and 1 black. So the probability of the first ball being white, given that the first ball was white, goes right back to 2/3. And the probability of F and S would be now 2/3 times 2/3, which is 4/9. So in our tree diagram to the right, we still have for the first row the 2/3 and the 1/3. And because we've replaced, our sample space is the same. So to get a second ball the second time would be 2 out of 3. A black ball would be 1 out of 3. And the same if we chose the white ball. If we chose the black ball first, it would still be 2/3 for a white and 1/3 for a black. So now, for white and white would be 4/9. White and a black would be 2/9. A black and then a white would be 2/9. And a black and then a black would be 1/9. Here, events F and S are independent because the probability of S is not affected on event F occurring. Let's summarize what we've just done. The multiplication rule. The general case is that the probability of A and B would be the probability of A times the probability of B, given that A has just occurred. We can change around this formula and make it the probability of B, given that A has already occurred, to be equal to the probability of A and B divided by the probability of A. If we just think about this for a minute, it makes sense. The bottom part of that probability is the sample space. And if you recall, the sample space changes once the first event has occurred. For the second part, a special subcase where events A and B are independent. The probability of B, given that A has already occurred, would be the same as just probability of B. And for independent events, the probability of A and B is just equal to the probability of A times the probability of B. Two events that are not independent are called dependent. Example 1. Two cards are drawn without replacement from a shuffled deck of 52 cards. We're going to find the following events as A being the first card is a face card, so A bar would be that the first card is not a face card, and B, the second card, is a face card, and B bar would be that the second card is not a face card. The first thing we're going to determine is the probability of A and B. Now I have a tree diagram drawn to the right. We probably don't need one in this simplified example, but let's fill it out anyway. So the line of A and B is what we're looking for. And if you notice that A, the probability would be 12 face cards out of 52. Now we've used up a face card and we've used up a card. So that would be 11 out of 51. We multiply these together to get 132 over 2,652, and we could simplify this to 11 over 221. Now we're going to look at the pathway of A bar and B. So A bar being that the first card is not a face card, and there's 40 cards that are not, so that would be 40 out of 52. The second card we do want to be a face card, and there's 12 still in the deck, but there's one card missing. So that would be 12 out of 51. Multiplying these together, we get 480 over 2,652, and this again can be reduced to 40 over 221. Example 2. Two cards are drawn without replacement from a shuffled deck of 52 cards. What is the probability that both cards are hearts? I'm using H here to represent that the card is a heart, and an H bar to represent that the card is not a heart. I'm going to be completing the tree diagram on the right as we go through. The first thing we're looking for is the probability of two hearts. So we've got 13 hearts in the deck, so it's 13 times 52. One heart is now gone, one card is gone, so we'll multiply that by 12 over 51. We get 156 over 2,652, and that can be reduced to 1 over 17. Now we're going to do the line of neither card is a heart. So H bar, and we have 39 cards that are not hearts, so that would be 39 over 52. We've lost one of those cards and we've lost a card in the deck, so we'd multiply that by 38 over 51. We do the multiplication, we get 1,482 over 2,652, and this can be reduced to 19 out of 34. For the last one, where we want exactly one of the two cards to be a heart, we can do this in one of two different ways. We can think of this as the complement, so that would be 1 minus the probability of two hearts, minus the probability of neither being a heart, which were the two answers that we got from A and B. Or we could do two cases. The one where the first one's a heart, the second one is not a heart, and add it to the probability of the first one not being a heart and the second one being a heart. So for the first one, let's look at the complement. We would do 1 minus 156 over 2,652 minus 1,482 over 2,652. We would get 1,014 divided by 2,652, which can be reduced to 13 over 34. The other way would be the probability of H bar. We'll figure that one out first. So that would be a heart and then not a heart. So that would be 13 over 52 times 39 over 51. And then we'll add that to the probability of not a heart and a heart. And that would be 39 over 52 times 13 over 51. And we get the same result as we got by doing the complement. Example 3. 3 cards are drawn without replacement from a shuffled deck of 52 cards. What is the probability that all 3 are spades? This is very simple. We've got 3 events, the first card, second card, third card. We want a spade for each one. So the probability of 3 spades would be 13 out of 52. 1 spade is gone and 1 card is gone. So we'd multiply by 12 over 51. Now we've got another spade gone and another card gone. So that would be 11 over 50. So 13 over 52 times 12 over 51 times 11 over 50. I'll leave you to continue on and get a final answer for that one if you wish. Example 4. Randomly select 1 bill from pot A and 1 from pot B. What is the probability of getting? The first one would be a $10 bill on each draw. Notice that these two events will be independent. It doesn't matter what we draw from pot A, it's the same probability for any of the possibilities for pot B. So we just really have to do the probability of getting a 10 out of A and then getting a 10 out of B. So the probability of 2 10s would be 1/3 times 2 4ths. This equals 2 over 12, or 1 over 6. Now we want a $10 bill on one of the 2 draws. So we'll split this up into 2 cases. We'll split this up as where we get a 10 on the first draw and then not a 10 on the second. Add it to the probability of not a 10 on the first one and a 10 on the second one. So for a 10 on the first one would be 1 over 3. Not a 10 out of the second one would be 2 out of 4. We'd multiply those two together. And we would add that to the probability of not a 10 out of the first one, which is 2/3, times a 10 out of the second one, which would be 2/4. And by completing the calculation, we'll get 6 out of 12, which can be reduced to 1 over 2. Our last example, example 5. A die is rolled 3 times. What is the probability of getting a 5 on all 3 rolls? Now each roll would be an independent event, and to get a 5 on a 6-sided die would be 1 out of 6. So for 3 rolls, it would be 1 over 6 times 1 over 6 times 1 over 6, and that would give us 1 over 216. For part B, we want at least 1 5 on the 3 rolls. So let's think of this as the complement. It would be 1 minus the case of rolling no 5s at all. So to roll a non-5 would be 5 out of 6. So it would be 1 minus 5 over 6 times 5 over 6 times 5 over 6. This gives us 1 minus 125 over 216, and a final result of 91 over 216.